Okay, thank you everyone for being here after lunch, and thanks to the organizers for organizing this wonderful conference and for the chance to talk here. This is joint work with Eric Insko, who is or was at Florida Gulf Coast University. He is moving, and I have forgotten where he's moving to, but it is a small college in Iowa. And Martha Prekup, who's at Washington University and would be here except that she has a newborn. Okay. So I want to talk about regular, minimal, indecomposable Hessenberg varieties, and I'll define what a Hessenberg variety is and what all those words mean in a moment. But I'm going to start with give you some motivation, and sometimes I think that for the purposes of this work, this motivation is really kind of fake, but this is the kind of thing that you should all know anyway. So I will tell you. And then I'll tell you about Hessenberg varieties, what they are, and about a cell decomposition, by which I mean an affine paving. So this is, again, not a CW complex, like in what Sarah was talking about this morning. And then I will tell you about, in this case, a regular, minimal, indecomposable, whatever that means, Hessenberg varieties. I'll tell you about how cells close to each other, some things about their cohomology classes, and some things about their singularities. Okay, so this is all background. Stanley-Stembridge conjecture, you can see it's an old conjecture from the 90s. It says that if you take certain graphs and take the chromatic symmetric function, so the chromatic symmetric function, you take every coloring of the graph by positive integers. You know, this is the usual graph coloring, so neighboring vertices have different colors. You assign to each coloring the obvious monomial, which is you just take x1 to the number of ones, x2 to the number of twos, and so on. Add up all the colorings. This is a symmetric function because obviously if you change the labels on the colors, you still get a coloring. Okay? And Stanley and Stembridge conjectured that for certain graphs, namely the incomparability graphs of 3 plus 1 and 2 plus 2 free posets, again, whatever that means, you get an E-positive symmetric function. Okay? So if you write it in terms of the elementaries, you get something with positive integer coefficients. Okay, Mathieu Guy-Paquet showed that, in fact, you don't need to prove this for all 3 plus 1 and 2 plus 2 free posets. 3 plus 1 free posets, you can prove it for 3 plus 1 free and 2 plus 2 free posets. Because the ones for 3 plus 1 free posets are convex combinations of these. Okay? And since the ones for 3 plus 1 and 2 plus 2 free ones are positive, if you can prove that, then that proves all the ones for 3 plus 1 free because those are convex combinations. And 3 plus 1 and 2 plus 2 free posets are very nice. There are only Catalan many of them. You can biject them with your favorite Catalan object. In this case, the correct Catalan object to think about is unit interval orders. So you have a bunch of intervals on the real line, each of length 1. Okay? They start at various places, A1, A2, A3, up to AN. And you simply say that one interval is less than another. So your elements in the poset are your intervals. One interval is less than another if it's to the left and doesn't overlap at all. I'm sorry. Right. Okay. Now, we take the incomparability graphs. So the incomparability graphs is we connect two edges if those things are incomparable, what you would think. Okay. Okay, so we reduce 3 plus 1 free to 3 plus 1 and 2 plus 2 free. Because the 3 plus 1 free ones are convex combinations of the 3 plus 1 and 2 plus 2 free ones. Okay. Now, if you have a unit interval order, that's completely determined by the data of, we have this interval. What's the leftmost interval that it still overlaps with? Because it's going to overlap with all the other ones because I've put them in order. Okay? So, or actually, I think I want the data of the first one that it doesn't overlap with. Okay? So I can encode this with what's called a Hessenberg function, a function from 1 to n to 1 to n, so the set of intervals to the set of intervals. And what are the properties that this has? Well, every interval is going to overlap with itself, so it, function h of I has to be bigger than I. Okay? And h of I has to be smaller than h of I plus 1 because this interval is to the left of the next one. Okay. So we're going to look at these functions. And they correspond naturally to unit interval orders. So maybe this is the Catalan object that we should think about. Okay, and now to such a function, I'm going to associate a variety that's inside the flag variety. Okay? Actually, a bunch of them. I'm going to pick, for now, a general matrix X. Okay? N by n matrix X. It acts on a flag by simply multiplying all the components of the flag. Well, I take X, and I'm going to insist that when I multiply by the ith component of the flag, I end up inside the h of ith component of the flag. Okay? So I have, my line is required once I hit it with X to lie inside, h of 1, which might be 3. So my line, once I hit it with X, has to sit inside my 3 space. Okay? That's what this would say. And so on. Okay? So I'm going to have this condition for every one of them, and some of them are going to be redundant. You can think about this carefully. That's right. Yes, now you can forget about unit interval orders. Okay. We've already passed from Stanley-Stembridge land to Hessenberg land, and now we can forget about unit interval orders. That was just motivation. It'll come back in a moment to say what exactly the motivation is, but okay. So we just now have to think about Hessenberg function, and the Hessenberg variety is the set of flags satisfying this condition. This has a notion for generally type. Okay. Let me tell you what it is. So instead of picking a Hessenberg function, I pick a subspace of the Lie algebra that's closed under bracket with B and closed on and in particular, that means it's closed on the bracket of H. Okay? And then I look at all the group elements that when you hit this X, which is also an element of the Lie algebra, okay, right? It's an n by n matrix. You can think of it as the element of the Lie algebra for GLN. So when you hit G inverse on X by the adjoint action, that's what this conjugation is in general, you land inside your Hessenberg space H. Okay. Now I'm not going to do it here, but I could take 10 minutes and show you exactly why this is somehow equivalent to the previous definition. It's just a matter of rank conditions on certain matrices, and exactly what this multiplication is tells you something. Okay. All right. So H becomes the space of matrices. So you should think H is going to be something with a partition cut out of the bottom. Okay. And H will be a space which is 0 on this partition. And H is the function that tells you the height, how many boxes are not in the partition in each column. Okay. So I'm going to do everything in this talk in type A, but people who have read this and understand what other types are can just basically figure out how this all works in other types, and almost all of the talk has a type 3 proof. Okay. And I should say, even in type A, this definition gets us something very nice, which is that it tells us that when we translate my Hessenberg variety by a group element, that just gives me a Hessenberg variety for a different X. Okay. I just conjugate X by the group element, and now we're just talking about another Hessenberg variety. Or you can think, we really only care about the conjugacy class of x, because if we conjugate x by something else, we just move around my Hessenberg variety a little bit. Okay? So moving my Hessenberg variety is just conjugating by my matrix by the group element. And I should say, the reason you need your Hessenberg space H to be closed under bracket is so that your G actually sits inside B cosets. That's exactly the notion that makes this actually come from something in the flag variety rather than something inside just GLN. Okay, so let me tell you why, what this has to do with chromatic symmetric functions of graphs. So Shereshian and Wax, they conjectured, this is about 10 years ago now, a little more, and it was proven by Brosnan and Chow and independently by Guic-Paquet that the chromatic symmetric function is exactly the Frobenius characteristic of the cohomology of the Hessenberg variety. Okay? And I have to tell you what X is. X here should be a diagonal matrix with distinct entries. Okay? So we have a diagonal matrix with distinct entries for that X and the Hessenberg function that corresponds to the unit interval order. Then the Frobenius characteristic. So Frobenius characteristic means that you decompose it into irreducibles and think of your irreducible V lambda as represented by the Schur function. Then the chromatic symmetric function is in fact equal to this cohomology ring. Oh, I have lied to you. There's an omega sitting there. I have to change E's and H's and so on. Okay. I tend to think that really this is because somehow like chromatic symmetric functions are defined wrong. Okay, and here's the nice thing about Frobenius characteristic. H's are the images of induced representations. And induced representations are special in this way, namely that they have a basis that's just permuted by the action of Sn. Right? Normally, if you have a representation, your group has some matrix, and it's going to be some horrible thing with lots of entries, various places. For the induced representation, your matrix is a permutation matrix or partial permutation matrix. Okay, so all your a permutation matrix. So all your elements of Sn, they just send one basis element to another basis element. Okay. Representation theory of linear algebra goes away from the representation theory. It's just combinatorics of the representation theory now. And so here's the dream proof of the Stanley-Stembridge conjecture, which is still open. You look at this cohomology ring, and you find a basis in it where this Sn action, which I haven't told you about, but you know it's out there, just permutes my basis. Okay. What's the holdup? No one can find such a basis. Okay. No, I mean, so for example, for the case of a path graph, that's the case of the permutahedral variety that Vasu talked about Sunday. That case, people know how to do this, for example. Okay. And I think there's a recent paper still in refereeing that purports to find such a basis. So it was proven by other means already for that graph. That's right. For any n. Okay. So these things come with an affine paving. Okay. Right. We're in a world where we like to have nice bases of our spaces, and this is one way of getting a nice basis of our space. It has an affine paving. And assuming your x is like one of the x's that you would think about rather than some weird conjugate of the x that you would think about, then your affine paving is just intersecting your space with Schubert cells. Okay? So you take your Hessenberg variety, assume that you have a reasonable X, like a diagonal matrix or something in Jordan form. Okay? Intersect it with Schubert cells. Some of them are going to be empty. You throw those away. And then some other Schubert cells, you're going to get the whole Schubert cell. And most of the time, or well, most of the time when it's not empty, you're going to get some subspace of the Schubert cell. Okay, so some cell of some dimension. So Juliana proved this in type A. That was basically her PhD thesis, 20 years ago. Martha proved this for other types almost always. There are a few really weird exceptional cases that weren't handled. This is basically her PhD thesis 10 years ago. But we're not going to worry about those really weird types. Okay? And it's not a particularly type. It's like some particular conjugacy classes of matrices in type D is the only cases that aren't handled. So that means that, well, one way of approaching getting a basis for this is, do the Schubert calculus thing, which is take this geometric basis and try to understand what in the world it is. Okay. And the approach here that we are basically just very much starting, because we're only going to do this for a few Hessenberg varieties, is we want to understand the image of this basis inside the cohomology, in the homology of G mod. Okay? And I say homology because these things are not necessarily smooth. I don't really want to think about cohomology on those things because we don't have Poincare duality. I don't exactly know what I mean by class of a subvariety in a cohomology. Now, there is a problem here, which is that the map into homology of G mod B is not injective. Okay? Lots of different classes go to the same class. So you're going to lose some information just from understanding its image in G mod B, but you don't lose all the information. In some sense, there is a problem that for the Stanley-Stenbridge conjecture, you lose all the interesting information because actually what mapping to G mod B does is it takes exactly the SN invariant part of your homology. Okay? The action that's on the Hessenberg variety, in the case of the full flag variety, it boils down to the action of actually multiplying by permutation matrices. That's trivial since permutation matrices have a homotopy to the identity inside the group. Okay? No, the trivial representation. For the flag variety itself, I'm trying to understand the trivial representation of dimension and choose 2. Okay? So it's not the action on the flag variety that you think, it's the trivial action on the flag variety. If you look at equivariate cohomology, then the action does survive. Okay? But this is the action that goes away when you look at ordinary cohomology of the flag variety. Okay? So this map of homology groups is SN equivariant with respect to this action. So exactly what's happening is that you lose all the interesting stuff. Oh, well. But I should say everything we're doing, like we haven't done it yet, but it makes sense in equivariate cohomology. None of our tools are failing in equivariate cohomology. So at least we do get that information as well. Okay, let me tell you the adjectives in the title of the talk now. Regular means that X is a regular operator. Means that when you put it in Jordan form, all the eigenvalues are different. Okay, so almost everything is regular. Minimal indecomposable means that I'm taking a particular H. It's the H where H of 1 is 2, H of 2 is 3, H of 3 is 4, H of 4 is 5, and so on. Okay? H of n has to be n. Okay? And if you want to look at the partition picture, this is the partition picture where you include the upper triangulars plus one little strip. And if you're interested in other types, that's exactly the root spaces of the negative symbols. Okay, so there are two like well-studied cases of this. If you take this particular H and X being the regular semi-simple element, this means that you just have a diagonal matrix with different eigenvalues. This is the permutahedral variety, the toric variety of the permutahedron. Okay, this is the case that was worked out, and in some sense the inspiration for thinking that the Stanley-Stembridge conjecture had anything to do with this sort of thing in the first place. And then there's the Peterson variety that Dale Peterson studied for various reasons connecting affine and quantum stuff and so on. It is part of that story, where X is regular nilpotent, so you have one eigenvalue. You can think of this as, if you want Jordan form, this is the matrix where you have, sixes down the diagonal and ones right above. And sixes could be anything, could be 0 if you want. I guess Peterson did the 0 case, but they all behave the same way. And from now on, instead of worrying about X in general, I'm going to just assume it's in Jordan form because I don't want to have to think about slightly, trying to state my theorem slightly more generally. Okay. Let me get into the combinatorics of which things exist and which things don't exist. Okay? So you have a non-empty intersection. I'll do an example in the next slide. You have a non-empty intersection if you don't have long inverse descents inside the Jordan block. I'll show you on the next slide exactly what that means. And if you're non-empty, your dimension is the number of descents, usual descents. This is in the minimal indecomposable case. Okay. All right. Let's take this Jordan form. Alpha and beta are two arbitrary complex numbers. They cannot be the same because this has to be regular. Okay, 3, 4, 2, 1, 5 is not admissible. Why is it not admissible? It's not admissible because you have a 3 and a 2, and 3 and 2 are in the same Jordan block, right? Your Jordan blocks are 1, 2, 3, and 4, 5. Okay? 3 and 2 are in the same Jordan block, but the 3 is more than one spot to the left of the 2. Okay? That's the combinatorics. If you have two numbers in the same Jordan block, if you have I and I plus 1 in the same Jordan block, and if I plus 1 is more than one spot to the left of I, then you're no good. It can be to the right. It just can't. It can be one spot to the left. It just can't be further to the left than that. Okay. Now let's see what these things look like. Let's look at this particular Schubert cell, and I have done this in columns. Okay, so 4, 1, 5, 2, 3 is the Schubert cell where the first, the line or the point in the flag, depending on which way you want to think about it, the point in the flag is the span of the first column. Okay, and the line is the span of the first two columns, and so on. So this is the Schubert cell, which you've seen. Okay, the usual B orbit of this point. All right, and let's see what happens if you impose the condition that this matrix times stuff is inside the span of U and the next flag. Okay, so let's look at the first column. When I multiply that column by X, what do I get? Well, I multiply the first 3 entries by alpha and the second last two entries by beta, and then shift everything up 1 and add those two results. Okay? So let me just write that down. I get alpha A plus B, alpha B plus C, alpha times C, beta times 1 and 0. And I need this vector to be in the span of the first two columns, and that tells me that B and C both have to be 0. Okay? I do the same thing 2 columns later. That tells me that E has to be 0. I should say this is a particularly nice example you don't get just coordinates have to be 0 in general. You get nastier things. You get, but it's always an affine a linear subspace of this in the right sense. Okay, and you can come up with a parameterization. Okay, here's the key observation in this talk, in this example. This is messed up. I have to figure out how it's messed up. Yes, the third and fourth rows of this matrix should be switched. I'm sorry. Okay. Third and fourth rows of this matrix should be switched. If I hit this guy with this permutation matrix on the left, I'm going to get this thing with the third and fourth row switched. And because B, C, and E are supposed to be 0, this actually lands inside the Schubert cell. Okay? And so let me state what happens in general here. And I need a little notation. Okay, I have a permutation W. I'm going to look at all the descents, the normal descents, one number bigger than the next number. I'm going to look at the parabolic generated by those descents. Okay? And I'm going to take W. I'm going to take W and multiply by whatever V is necessary to make it the longest element in that parabolic subgroup, or the maximal length representative for the identity coset, if you like that one better. Okay? So I have 4, 1, 5, 2, 3. Its descents, it has descents in the first, between the first and second spot, between the third and fourth spot. So I should hit it with whatever is necessary to make it 2, 1, 4, 3, 5. Okay. And the lemma is, if you hit it, then you actually land inside the Schubert cell. And the Hessenberg condition just gets, well, when you move around a matrix, right, I said you just conjugate the x. Okay? All right. And this works for closures. Remember I said at the beginning we really want to understand closures here. Now you might ask, why in the world do I want to hit it to something like this? Well, these W not P's, their Schubert varieties are just little flag varieties. And little flag varieties, we understand Hessenberg varieties sitting inside little flag varieties. They're just Hessenberg varieties. Okay? So now the closure, instead of this intractable problem involving whatever, now is just like, what's the closure of the big cell of a Hessenberg variety inside of a Hessenberg variety? Well, you know, these Hessenberg varieties are irreducible, so we know what it is. Okay, so you have a W, you have an X and Hessenberg variety, a regular minimal indecomposable Hessenberg variety. You translate it by V, you end up with a Hessenberg variety, a smaller Hessenberg variety. Either you say it's a Hessenberg variety if you don't insist your groups are simple, or you say it's a product if you do insist your groups are simple. Okay. Now that you've got this information, you know, you basically can work out what Sarah called this morning the two orders that Sarah talked about this morning. Okay, right? There was the espresso order and the medium roast order. Those make sense for any time you have an affine paving. Okay. So you want to know, when is CW intersect? When is the closure of a cell hit some part of another cell? Won't necessarily be the whole thing. Okay. Well, it's going to be non-empty if and only if it's in the same coset, and smaller in Buchau order, and non-empty. Okay. And what's the dimension? Well, the dimension is the number of descents inside a descent block of W. Okay? So U here can have extra descents that did not come from a descent of W. Okay? So descents of U that are in the same places as descents of W. Okay? And if every descent of U is in the same places as descent of W, then it's contained inside the closure. And if it's not, then some part of it is in the closure and some part of it is outside. Okay, here's the same example, 4, 1, 5, 2, 3. X is regular of Jordan type 3, 2. Then now you can think about what all the things in its closure are. So you can swap the 1 and the 4, you can swap the 5 and the 2, or you can swap both. You swap the 1 and the 4, you get something of dimension 1. This is entirely inside here. You didn't produce any extra descents. Okay? All the descents here were descents here. 4, 1, 2, 5, 3, you swap the 2 and the 5. Well, now you have one descent left, but you somehow produce an extra descent. That descent doesn't count. Okay? But that extra descent tells us that this cell inside the Hessenberg variety actually has dimension 2. So you didn't actually, not the whole cell is inside the closure, only one dimension of it is. And then you can flip both and same thing. Okay. Let me tell you what this means for cohomology classes, because that was the original motivation. And I want to say, right, I want to do, in some sense, I want to do Schubert calculus on these things. I have this basis. And I want to do Schubert calculus in some sense correctly with a geometric basis. Leo is back there, right? He wrote a paper with Rebecca and Raful Singh telling us how to do Schubert calculus by basically pulling back the right things in the Schubert basis from the flag variety. I don't want to do that. I really want the geometric basis. Okay. Okay. I want to do Schubert calculus on this cohomology ring. That means I need a basis. Okay. If I want to do it geometrically, then I want to do it with this particular geometric basis. Classes of the cells of closures of cells. Right? You can, and maybe it makes sense to because it's easier, at least in some cases, cheat by instead of taking geometric classes of cells, pulling back classes from somewhere else, like the flag variety, and pulling back the right collection of classes from somewhere else and taking that as your basis. Okay? All right. Well, oops. This is actually a formula that you might not have known for the class of one of these little flag varieties sitting inside. Okay? You might not have known this because in some sense it's a terrible formula. There are minus signs you have to reduce by the ideal, right? They're not the Schubert polynomials. Okay? But they work very nicely here. It tells you that if you have any W, you translate it to W naught, but this W naught thing, but W naught thing, you can just read off the descents of W. Okay? So P is now the parabolic generated by those descents. So there's a fraction here. This is actually an integral class. Doesn't look like it, but it is. You multiply by all of these, plus you get a bunch of these coming from the descents. Okay? And I don't think Vasu told you on Sunday, but that was the original motivation for his work, is actually understanding what this is in Schubert classes. And they have more or less solved this problem. Okay? So if you want to know what this is in Schubert classes, you go ask Vasu or Philippe. It is only the xi minus xj's, but it extends easily. I think I have convinced Vasu that it extends easily to this case. Okay? They did just the big cell, the class of the big cell, but now we're just talking about the same cells in littler flag varieties. Patient. Sure, why not, right? But if you want to express it in terms of Schubert polynomials, yeah, right. And right, this is always one of those questions where when you ask it and you work on it, you're like, is this a stupid question? But now Vasu and Philippe have gotten such a nice answer, it is not a stupid question, obviously. Okay, I want to point out, first of all, this formula is completely, the Jordan type of X doesn't appear anywhere in there. Okay? It doesn't matter which Hessenberg you're working in. Of course, it does matter that if you're working in the wrong Hessenberg, this thing is actually empty, and I was telling you, lies about nothing. Okay. And also, it completely doesn't depend on what W actually is. It only depends on what its descents are. Okay. So cells that come from W with the same descents are actually homologous to each other. This is exactly what's going on in that the homology is not injective, that these cells are collapsing to each other in the homology of the flag variety. Okay. I do want to say something about what happens in the cohomology ring of the Peterson variety. Okay. That is the case where it is injective. Okay. And even though the Peterson variety is not smooth, it does have Poincare duality, at least rationally. Okay? If you do Q coefficients, you have Poincare duality. And well, if you take W to be the long word, you get none of the things on the right. Right? You have all descents. You get none of the things on the right. You take W to be a long word. Well, what I want to say is that all of these are products of the class of the Peterson itself with more stuff. So that means that if you want to do Poincare duality by thinking about cap product, right? The rest of the stuff is what you cap with the class of the fundamental class. You get your thing. So I'm hedging myself a little bit simply because this isn't actually a smooth manifold, and I can't talk about Poincare duality legitimately, but this is Poincare duality. Okay. So, oops. In particular, this means that all your classes are rational multiples by this thing of square-free monomials in these. Okay? And these are the generators that Kliashko. He didn't quite put it this way, but Kliashko used to study the cohomology of the Peterson. Okay, I've got 9 minutes left. Let me tell you something about singularities. Okay, so here's what I can tell you. We know which permutation flags are singular points. This thing is bad enough that right in the Schubert world, there's this group action. If your permutation flag is a singular point, you use the group action to move everywhere else in the cell. You know that the whole thing is singular. We do not have a group action here. Sometimes you have smaller group actions that get you little bits of things, but you don't even get that. So it turns out that you can have a case where the permutation flag is a cell, is singular, but the rest of this cell is not singular, or only some of the rest of this cell is singular. Okay. All right, if you have a right coset that keeps all your Jordan blocks together, and on the next slide, I'll show you what exactly I mean by that, and then permutes the Jordan blocks with each other, but doesn't break them up. Then you look at the rule for Petersons that Alex and Eric worked out more than 10 years ago, 15 years ago. And compare that with what's happening in this coset. That's the answer. That's also true in other types. The Peterson rule wasn't worked out previously in other types. We spent way more effort than we really should have trying to figure out what the rule is in other types. It turns out that in other types, in all of the other types other than B, only the top cell is non-singular, the rest of them are singular. And in type B, the top cell and the cell corresponding to the thinking node that's far away from the long word is all the Petersons are complete intersections. In fact, all regular Hessenbergs are complete intersections. Okay? That's how we prove all of these things. All of these things are complete intersections. We analyze their equations and what the tangent space is. Okay, and if you're not in one of these complete cosets, so the other cosets will be smaller. There will be fewer non-empty cells inside those cosets. Automatically, fixed point is singular, but there might be other non-singular points. Okay. I couldn't do 3-2. That would take like 3 times as much space or something like that. So here's 3-1. All right, here's what I mean by Peterson coset. These are the 2 Peterson cosets, and inside these 2 Peterson cosets, the numbers 1, 2, and 3 are next to each other, and the 4 is at either end. Okay? So Peterson coset means that basically I permute the blocks, okay, and keep them intact. So these form a Peterson coset, and if the rule for Peterson says that this is a singular point, and everything else is smooth. Okay, the top 3 things are smooth, everything else is singular. These are non-Peterson cosets. You can see this has length, this has dimension 2, this has dimension 1. Remember, number of descents. Okay, but each one of them has a one-dimensional singular locus. So in the 1, 4, 3, 2 case, well, a Peterson coset is one where the let's take the minimal coset representative, and you multiply it by something to get all the other ones, right? So a Peterson coset is one where those permutations are all the permutations indexing things in the Peterson variety, intersectional cells of the Peterson variety. And those are the biggest ones. Okay? The other ones, the restriction on long inverse descents will force you to not have certain things. Like, for example, right here, in this coset, I can't put the 2 before the 1. I can't swap the 2 with the 1 because now that's too far. Okay? So the non-Peterson cosets, their permutation flags are always singular. But like this cell, it's a 2-dimensional cell, but only 1 dimension of it is singular. Some line inside that cell is singular, the rest of it isn't. This is another non-Peterson coset. Here is only a 0-dimensional singular spot, but this one is all singular. Okay? All right. And the surveys, right, you have. And by the way, the singular locus is disconnected. Okay? There's this point is a singular point that's completely isolated from all the other singularities. So these things are not, not as nice as you might hope. Okay, I think that's it. Thank you.